sir. This is the same section. It is still 6.2. It's the second half of 6.2, just so you guys know. I didn't want to try and cram all of this in the same section.
6.2.
6.2.
6.2. I put 6.25.
6.25.
Sure.
I put 6.2.2.
Whatever you want. What I'm looking at here today is talking about the graphs. And eventually, you will be graphing all of these with and without a calculator. But what I want to look at today is something that's a little bit different. Something we haven't really talked about before. I want to look at what's called end behavior. I want to look at end behavior of graphs. No. The end behavior. End behavior is nothing more than what's happening at the tails of the graph. Now, we're talking about all functions here. We're not looking at anything that's not a function. So every single graph is going to have some sort of behavior at the end. Now, the book writes this backwards. So be careful when you read it in your book. It's worded a little bit differently. But I do want to just kind of relay this end behavior to a little bit of what we were working on with synthetic substitution. If you remember with the synthetic substitution, we had a function, f of x, let's say it was x cubed plus 2x squared minus 1x plus 7. And we were substituting in what is f of 3. What we were doing there is that we were saying 3 was going to be the x value, and f of x became the y value. They were ordered pairs. Your ordered pairs would have been 3, comma, whatever f of 3 was. And that was your ordered pair, okay? So what that tells you is the function f of x is synonymous with y equals. It basically means the same thing. It's your h and your k. Your h is your x, your k is your y. This is getting you an ordered pair. That's how synthetic substitution works. What I want you guys to take from that is when you're looking at a graph, you have your x-axis and your f of x axis. Is that okay? Does that make sense?
Yeah.
F of x is synonymous with y. So if I want to say the f of x axis means the same thing as the y axis. Sometimes it's a little bit difficult to comprehend. So with that idea happening here, if we had this this graph, x cubed plus 2x squared minus x plus 7, and let's just say I wanted to get a rough idea what that looked like. Oh, what was it? X
cubed plus 2x squared.
I forgot this. X cubed plus, sorry, 2x squared.
Yes. Minus x plus 7.
Okay. So if I just look at this graph, just for fun.
Oh, what? That's great. What?
This graph is basically going up, change directions, and continuing. Everybody kind of see that?
Yeah.
All right. So as what I want to do here is that when I substitute in for 3, if I do that, I'll get my ordered pair. If I substitute 4, I get a different ordered pair, 5, and so on and so on. What I want to ask you guys is, as x is getting larger, as x approaches infinity, as x is going this way, what is f of x doing? It's going up, so what is it approaching?
Infinity.
Positive or negative infinity? Good. So in this graph, as x approaches infinity, f of x is approaching positive infinity. That's what end behavior means. What is happening to the tail of the graph? As x gets bigger, y is getting bigger. On the other hand, as x is getting smaller, as x is getting smaller and smaller and smaller, as it's approaching negative infinity, what's happening to f of x? It's also getting smaller. It's also approaching negative infinity. That's end behavior. What's happening at the tails? What are your graphs doing at the very ends of them? I know, ooh, it's got jazz hands. All right. Well, if you keep looking at it and you tilt your head just right and look down, you might be able to see it. Okay. That's end behavior. What's happening at the tails of the graphs? So you can, depending upon what the graph is, your end behavior is going to change. The only thing that doesn't change is the following. X is always getting bigger, and x is always getting smaller on that side. Do you agree?
Yes.
So depending upon what your graph is doing, your end behavior might be different. For example, what's your end behavior? As x is approaching positive infinity, what is that? Good, so I wouldn't say y though, I'm trying to talk in function. F of x. Okay? As x is approaching negative infinity, what is f of x approaching in that graph? Whoa, this is pointing down. It's also approaching.
So that rule you just talked about, only for that last graph.
Each graph might have something different.
Oh, that need to reach that.
Okay?
Wait, so x is always approaching both infinities?
Yes.
Like no matter what?
No matter what, because you're going to look at both sides of the graph.
All right.
All right, you're always going to look at both sides of the graph. So basically your rule is here, you're going to look at a graph, as x is getting smaller and x is getting bigger, what's the other stuff doing? Yes, sir?
So if it's like making a circle, then
A circle is not a function. A circle isn't a function because remember how to tell something is a function? It has to pass the vertical line test.
Oh, yeah.
Does that pass the vertical line test?
no.
No,
Wait,
so it's
what
not a
is-
function.
Oh.
A vertical line test.
The line on 2 points.
Correct. Vertical line test tells you if it touches it in more than one spot, it's not a function.
So a sideways parabola is not a function.
A sideways parabola is not a function, correct?
But a regular parabola is.
Correctamundo. Yes, ma'am.
Would the only thing that like didn't pass the test would be a function be like vertical line itself?
Vertical line is not a function, correct? What's that? But a horizontal line is.
I feel bad because all these vertical things are.
I know, they're just undefined all over the place.
So
They have no meaning.
Yeah, what do we call those?
What?
If they're not functions, what do we call things that happen?
Not function.
Well,
A line is a
horizontal
function.
parabola.
Yes, sir, Mr. Allen.
So would a sideways parabola be a function if it was f of y?
What does that even mean?
What is the what?
Function of y. I don't know. I don't know. I don't think so.
But didn't he just say that y can be a function? A y?
No, I didn't say it like that. We were saying that the vertical line isn't a function. I would say. I'm not sure. I guess it depends on how the nomenclature is put out there, but if I ever learned that, I've already forgotten it because it might not have ever occurred, or the fact that I'm old.
We're talking about three-dimensional.
We don't talk about, we're talking in two-dimensional regular land off function. Okay? So let me show you this little trick. Does everybody agree when you're dealing with polynomials, you've got exponents? You've got something like that? Now, your exponents have two different things going for them. Your exponents can either be even or odd. Do you agree?
Yes.
Do you also agree that your coefficients can be positive or negative?
Yes.
So basically, I'm looking at 4 different scenarios, right?
Yes.
Okay. Let's look at something you already know. What is the graph of 2x squared going to look like? You don't need a calculator for this. You should be able to tell me off the top of your head. It's going to look like a graph. Correct. It's up like a cup, right? It's up like a cup. It's a parabola that's up like a cup. Do you agree? Whereas the other one, what is it going to look like?
Down like a
It's
frown.
going to look down like a frown. And why is it down like a frown?
Because it's got dimples on it.
Because the first term is negative. Do you agree? Okay. What do you think changes if that's a 4? Or if this is a 12?
It's gonna be like that other one, but it's like, like ups and downs.
Use your calculator. Look at your calculator. Type those two in your calculator. So we have 2x to the 4th. I'm going to show you guys how to put two functions in at the same time. 2x to the 4th. Hit enter, and then type in negative 2x, what did I say, the 12?
Yeah.
Okay. You can put in two different functions at the same time. And hit graph. There's your first graph.
I don't have any.
What?
And there's the second one.
I've got one.
You typed it in wrong then.
Oh wait, now I got two.
There you go.
I got two.
When it reaches.
Now, what's happening here is what you've already learned with a regular old boring quadratic. A quadratic is either going to go up or it's going to go down for the tails. You agree? When you get to the higher degree polynomials, as long as the highest degree is even, your tails are always going to be the same. There might be a lot of junk going on in between, in the middle, which is completely plausible, but your tails, what's happened at the end, will always be the same. So here's what happens. There's a nice little rule here. If you have an even degree polynomial, leading term is positive, your tails are going to be as x approaches positive infinity, f of x will also approach positive infinity. And as x approaches negative infinity, your tail will still be going to positive infinity. It's still going to be up like a cup. There's, thank you. Sorry. I did that last hour too. Your tails will still be the same. Okay? Your tails will be the same. I want to show you what this looks like graphically real quick. We all have 2x to the 4th in the calculator, right? Go back to your calculator real quick. And I'm going to turn off the negative x to the 12th. Here's how you do that. Scroll down one. Go over, so the cursor is blinking on the equal sign. Press enter, and it turns that graph off. Okay? Now let's go back up and add some other junk to that 2x to the 4th. Let's put in the next three parts it could have. So let's say we have minus 3x cubed plus 2x squared plus 1 or plus x minus 4. So I have a 4th degree polynomial. I put in 5 terms for it, so now it should look a little funkier. If I graph that, if I guessed right, there's some dips and dives to it. Guessing.
Absolutely nothing is showing up.
Your window's all sorts of messed up. Change your window to a 10 by 10. What's going to happen here is that eventually you're going to get graphs that are going to go up and down and do a lot of weird things. but the tails will be the same. If it's an even function, the first term is positive, your tails will always be pointing up. If it's an even function and your tails are, and your first term is negative, the tails are always going to be pointing where? They're always going to be pointing down. So if the leading term is negative, as x approaches positive infinity, f of x is also approaching negative. As x approaches negative infinity, f of x is going to approach negative infinity as well.
It's for still.
This is still for the same thing. It's just if yes, sir. First term positive, first term negative. No matter what, if you've got a whole bunch of other junk tacked on after it, you know, if we have negative 2x to the 12th power plus 9x to the 10th power minus 6x to the 7th power, blah, 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 you're going to have a whole lot of other junk going on in between the tail, but at the very end of it, it's still going to be pointing downward. Okay? Does that make sense? It's kind of a generic rule that always holds true. It will always, always hold true. So, if you have a degree that's even, first term is positive, think up like a cup. First term is negative with an even power, think down like a frown.
If x approaches negative infinity, if x approaches.
Yes, sir. Think down like a frown. Think of it as down like a frown.
Yeah.
That's all it is. That's what I'm thinking of here. All right. You can't draw a hyperbolic paraboloid?
What?
A Pringle? Potato chip? Hyperbolic paraboloid?
How does that look like? Oh,
That's what that is. Did I tell you that?
no, a Pringle I was gonna say, but I get it
There's
now.
Everybody knows what a Pringle is, right?
Yeah.
Did I tell you why they're made like that? A mathematician was really annoyed that he always had broken potato chips. So he thought about putting them into a canister so that way they wouldn't break. But if you stack a bunch of them together that are flat, they're still going to break from shaking around in the lab. So he came up with a structure. You guys know how like an arch is one of the strongest supporting characters? So you have a curve to it, and so he developed what's called the hyperbolic paraboloid, and that's the shape of a Pringle. You can stack all of them on there, and it minimizes the possibility of breakage. Because he was hungry. Math is useful. We got Pringles from math.
I don't like Pringles.
I don't like you, and I don't complain. Oh, I'm kidding, Andrew. No, I'm kidding. Anyway, I'm joking.
I don't care.
I know. Type this in your calculator. Put in f of x is x cubed. Well, look at that. Y equals. Okay. I'm going to look at the graph of y equals x cubed. I'm so glad you're easily amused.
So if you did, wait, time out. If you did, never mind.
Say it.
No, never mind.
Say it.
Say it.
Say it. Say it.
I forget what I was gonna say.
No, you don't.
So,
I forget.
see, yeah, okay, so if you did negative x cubed, then it would be the other part of it. Sorry, that was pointless.
Wait, what?
Then it and if you put those together, it makes the other part.
Right.
Is there the other part of the
Point of inflection.
where it
Change direction.
Whoa, that's cool. So not like we're changing the direction, but like if you couldn't have to be like that part.
Now, what's happening here? This is an odd powered graph. Everybody agree with that? Now, if you don't have any other things tacked down there, every odd power graph will look like this. If it's x to the 5th, x to the 19th, x to the 37th.
Well, what does the degree change?
The degree change,
Bigger.
it wasn't so much that. What happens is that you get what are called possible changes of directions, points of inflection. And we're going to study that later. Right now we're just talking about the basic, we're starting with the tail ends. We'll work to the insides eventually, okay? Now, these are odd functions. If I have an odd degree with a positive first term, as if I put this like this, not bad. As x is approaching positive infinity, what is f of x approaching in this case?
Oh, positive, because it's going.
I think you should stand up and do the dance.
I was looking at like the, so
Don't make excuses.
Yeah, I'm trying to make a t-shirt out of it. And then if I go, what were you saying, as x is approaching, f of x is approaching?
I get it.
And it's all visual. Same thing here.
Oh, so negative.
As x is approaching negative infinity, or excuse me, we do positive first. What's f of x approaching? Negative. Okay. Now, one of the things that's going to happen here is that, I may mention this a bunch of times, there will become more of a calculator, non-calculator portions of tests and things. You guys can type these things in your calculator, look at it, and say, okay, this is what's happening. I want you guys to be able to look at just a function and tell me what's happening without your calculator. There will be a time and a place for us to be able to look at the calculator to find what are called localized maximums and minimums, things like that. Don't get the heebie-jeebies. It's actually not that difficult.
All right.
You were talking about what are called those points of inflection, where it's changing direction. All that kind of stuff does occur. We have a lot of that, and we will be able to find those things. We're going to be able to find zeros of these functions as well.
At the point of inflection, it's just the plus or minus that you tack on.
Not necessarily. The plus or minus that's tacked on the end is your constant, which is your y-intercept.
That'd be the point of inflection.
No, sir. No, because what can happen here, let's see if I can draw this.
Hey, that passes
looks
the
like my
vertical line.
grades.
Looks
Looks like
I'm just saying that's a function.
It's a function, passes that vertical line test. If you look at this, it changes direction 1, 2, 3, 4.
So it could be a point of inflection.
There are multiple points of inflection here. We're going to find, eventually we will find those 4 points of inflection, because if it has 4 points of inflection, it means it had to have been a 5th degree polynomial. And if I'm looking at that, if this is a 5th degree polynomial, is that first term positive or negative?
Negative.
It's negative. And why is the first term negative?
X goes down, Y goes up, and Y goes up, Y goes down.
And it follows these patterns. Does that make sense, Andrew? I mean,
Yeah.
we're going to get to that point. Also, we'll be able to figure out what that is as far as the terms are. It would be negative something x to the 5th with x to the 4th, blah, 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 blah. And then I'll have a negative constant at the end because our intercept is here for I'm sorry, that's our 0. This is our intercept at negative something. Okay? Since there's 4 changes of direction, it's a 5th degree polynomial. It works very easy. We'll get to that point. All right? All I'm looking at today is can you look at this graph, or not even look at the graph, but can you look at this function? Exactly. And why is it going to look like the one we just saw?
It's negative. And then negative's gonna be
You know that it's going to go like this somehow, some way.
It's a 5th degree polynomial.
I don't know what it's going to look like, but I know it's... Yeah, you'll have a positive y-intercept, correct. So if you did sketch this, I know that I'd have a 0 here at positive 2. I know that would occur, but I don't know what else is going on in between. I could have just that one little dip and change. I could have a couple of dips and change. But all I'm looking at is, can I tell by just looking at this function what is happening as x approaches positive infinity and what is happening as x approaches negative infinity. That's what I want you guys to be able to do, just by looking at the equation. Okay? Yes, sir?
Is there a certain name for that function?
A fifth degree polynomial. That's about it. That's all it is. Your book says this backwards. They say as f of x is approaching negative infinity, x is approaching positive infinity. They look at the y values before you look at the x values. Don't do that. It is wrong. It's stupid.
That's just terrible.
It's just terrible. Yes. Darn you, old Algebra 2 book.
It's independent versus dependent.
Yeah, maybe
We're gonna
we
say
have
science.
2001 maybe?
Almost as old as we are.
I mean, math doesn't change all that often. I mean, some of the statistics stuff, I mean, what was,
Like a lot of the.
oh, sorry, 2004. Copyright 2004. So, yeah, it's only 10 years.
How often do you get
So,
those?
How much new stuff have they
They
come
don't.
out since like that was published?
really not that much, and that's why
I saw last weekend.
some of the nomenclature just changed a little bit, you know, how we write things a little bit differently. The pictures and the word problems they use with some of the data, I mean, they were talking about data with Mark McGuire's home run chase, really.
I love it. I love the pictures from the old books.
I like the picture, remember the picture of the girl with the cell phone that was like a brick? That was awesome.
There's these really funny pictures in our Spanish book. Oh, you're so bad.
Yes, they're all
I
like
love
big
them.
squares.
Like the first, the chick in the wheelchair, she's just like,
Chick in a wheelchair.
I'm gonna find it.
You know that chick in the wheelchair, that's funny. What is wrong with you?
Wheelchair.
Seriously?
Because there's like 99.
Tell me this is not hilarious. Look at her face.
Que paso?
She's like, okay, I'm gonna show this to the class. Look at this picture of this chick in a wheelchair.
Look at her.
Seriously?
Look at her on the other side. She's like this.
Yeah, and then in this one, she's like, I know.
And the news crew was probably.
You cannot tell me that's not funny.
Bless you, you're so unique. The other thing that we're going to look at here is, eventually when we get into these things, you will be able to use synthetic division to find zeros. Okay? At one point in time, when we get to these really, I don't know, people are just waiting.
That's Miss
I guess you can all. No, he's not.
Okay, if they have
No,
seen,
it's
they're
only
not
for like.
marking it. Yeah, you're a lucky guy.
Actually, my first teacher.
Eventually what's going to happen is, we're going to get to this point. If we do something like that, hey guys, what'll happen is we're eventually going to be able to know that this is going to be moving up, doing some other stuff and going up like that. We know our tails are going to be like this. The middle part, we don't know. But we know that the tails are going to look like that. Does everybody agree with me on that?
Yes.
We're going to be able to use synthetic division or synthetic substitution to get a 0 at the end. Because what we're going to be looking for is, if I put in 1 for x, I might get a 0 for y. So there's a method to doing it. It's a very easy method. And you guys all saw how fast it is to use synthetic substitution. Once you get used to it, synthetic substitution is one of the easiest ways to factor. You can factor. What's that?
To use it for anything.
Yes, you can. It's easier to use it for higher degree polynomials than it is the lower degree ones, because the lower degree ones, it should be easier to say, oh, what times what. But if you get to like a fifth degree polynomial, you can factor it real fast with synthetic. Okay? Yes, sir.
What are the problems gonna look like our questions?
For tonight?
Yeah.
Yeah.
Questions for tonight, it's on section 6.2 again.
Like, what are they gonna ask?
I'm gonna tell you.
Ask for
It's 334. I want you to do numbers 54 through 64 evens. And then I want you to do 81 through 86 all. Now, 54 through 64 is basically asking you what is the end behavior look like. So for these guys, you're going to get a graph, and I want you to write down as x approaches positive infinity, f of x approaches blank. As x approaches negative infinity, f of x approaches blank. That's what I want you to do for those, okay? The other part is looking at the graphs and the table functions in your calculator to help solve a couple of word problems. They're ridiculously easy. Okay?
Thank you.
Give those things a shot. We'll talk a little bit more about it tomorrow. Okay? Preguntas para clase de matemáticas.
I thought you were gonna say this clase de español and I was gonna cry.
What's that mean?
For your Spanish class.
Mr. What?
Your
What?
Spanish class.
Oh,
Class of Spanish.
I have a Spanish test today.
When is birthday?
To get it ready.
Cállate la boca, chica. ¡Wow! Soy es un negativo.
You said soy.
That means es posible.
My Spanish name is Raula because she didn't want me to have a guy name. And I want to be Raul.
Taking her chapter.
Me llamo Jefe.
Me llamo.
Jefe meant, no, Jefe means the boss.
Yeah.
Because that's the name they gave me in
Also
Spanish. So they gave me Jefe. I'm like, that's Jefe.
So you like really good at Spanish?
No. I had, all I know about Spanish, in my high school, I had 4 years of it. And my fourth year, it wasn't AP or anything like that. Our fourth year, our teacher was...
I can tell you.
Well, it's also 20 years ago, come on. Our teacher was retiring, so about halfway through the year, she kind of gave up a little bit. So we did a little bit more study hall than we did Spanish.
Wait, what?
We watched a little bit of... She's retiring. We watched a little bit. We tried to... I know, but this was 20 years ago, and she was done. We watched some... what do you call it? Soap operas in Spanish.